So in the last lesson, we established the equations of motion of a projectile, which connected its horizontal displacement, vertical displacement, and its initial velocity v0 and the angle of projection theta. Now in this lesson, what we'll try to do is find what is the path taken by a projectile as it moves up in the air. Or in other words, can we establish a relationship between the coordinate x and y of a particle as it flies up in the air? So to do so, we'll make use of two equations which we've derived earlier. First of these equations describes the vertical motion of the particle, and let's label this equation number 1. And this is vertical motion, and equation number 2 describes its horizontal displacement. Let's call this equation number 2, and this is horizontal displacement. Now you will quickly see that if you eliminate t between these two equations, you will get the relationship between x and y. So that's what we'll do. So in equation 2, if you see, t is equal to x upon v0 cos theta. And if we substitute this value in equation number 1, you will get the relationship between x and y. And this is the equation you will get. And let's call this equation number 3. And what you will observe is that this is the equation of a parabola. So you can write this equation in the form y is equal to ax minus bx square, and this is the equation of a parabola. So if you substitute the value of x in this equation, you will get a corresponding y value. So if you have, let's say, x1 over here, let's say this is your x1, then the corresponding y value can be found through this equation, and this value would be this. Let's call this y1. So that takes us to another very interesting part of projectile motion, and that is the range of a projectile. Now the range of a projectile is nothing but the horizontal displacement of a projectile when it reaches the same height as it was at the time of projection. So for example, if these are coordinates 0 and 0, then when it reaches the same height, which happens over here, then the horizontal displacement so achieved is called the range. So in this case, you can say that this coordinate would be nothing but the range r, and the elevation would again be 0 because it's back at the 0 level. So now how do you find this range? It's pretty simple. What you need to do is put y is equal to 0 in equation number 3, and that's what we'll do. So when you put y is equal to 0 in equation number 3, what you will get is tan theta x equals g upon 2 times v0 cos theta whole square times x square. And if you solve for x, what you get is x is equal to v0 square upon g times sine 2 theta. Now what you would see is that this range can change. It's variable depending on the angle of projection and velocity. So let's say if the velocity is kept constant, the range would change as the angle theta changes, and therefore the next obvious observation would be that what is the maximum range? And you will find that the maximum range would happen when this expression sine 2 theta is maximum, and we know from mathematics that the maximum value of sine 2 theta can be 1, in which case 2 theta should be 90 degrees or theta should equal 45 degrees. So we can say that when the angle of projection is 45 degrees, the range is maximum. And so we can write it over here that for theta equal to 45 degrees, the range is maximum, and this range, if we call it Rm, equals V0 square upon G. So that takes us to another interesting observation, and that is that if you project a body at an angle theta with a velocity V0, it would have a certain range. But there is another angle apart from angle theta at which if the body is projected, the range would be similar, and it could be shown like this. So for another angle theta dash, the range would be similar, which would be this. Now the relationship between theta and theta dash is that theta is equal to 90 degrees minus theta dash. So you have two angles of projection for a given velocity V0, which would give a similar range.